Question 12. Two unbiased dice, each with faces numbered 1, 2, 3, 4, 5, and 6, are rolled. What is the probability of a 6 appearing on at least one of the dice? Now this is a two-stage probability experiment where the second stage is not affected by the outcome of the first stage. So the first stage is the outcome of rolling die number 1, and the second stage is the outcome of rolling die number 2. And this can be modeled using a probability tree diagram, like so. So with die 1, there's two possible outcomes that we need to consider. We're either rolling a 6, and there's a 1 on 6 chance of rolling a 6, or we do not roll a 6. So rolling the numbers 1, 2, 3, 4, or 5. And there's a 5 on 6 chance of not rolling a 6. Now likewise with die number 2, now die number 2 is not affected by the outcome of die number 1. And the probability of rolling a 6 is 1 over 6, and the probability of not rolling a 6 is 5 over 6. And likewise for this part of the tree diagram, probability of rolling a 6 is 1 over 6, and the probability of not rolling a 6 is 5 over 6. Now there are three possible outcomes where at least one of the dice will show a 6. We either have 6, 6, 6, not 6, not 6, and 6. And the probability of rolling each of these is found by multiplying along the probability tree. So the probability of rolling a 6 and a 6 can be found by multiplying 1 over 6 multiplied by 1 over 6, which equals 1 over 36. The probability of rolling a 6 and not 6 is 5 over 36, so that's 1 on 6 multiplied by 5 on 6. And the probability of not rolling a 6 on die 1 and rolling a 6 on die 2 is 5 over 6 multiplied by 1 over 6, which is 5 over 36. If you add these three values together, these three fractions, that equals 11 over 36, and that's option B. Now there is another way to work this out, which is to consider the complement of at least one of the dice showing a 6, which is none of the dice showing a 6. And the probability of that is 5 over 6 multiplied by 5 over 6. And then we subtract that from 1. So the probability of at least 1 6 is equal to 1 minus the probability of not rolling a 6 at all. So 1 minus 5 over 6 multiplied by 5 over 6, and that equals 11 over 36. Answer is option B. Question 17. A spinner with different coloured sectors is spun 40 times. The results are recorded in the table. What is the relative frequency of obtaining the colour orange? Now, relative frequency is experimental probability, and the value of relative frequency cannot be less than 0, nor can it be greater than 1. So options C and D are automatically out. So to determine the missing value here, we know that the sum of the frequency column should equal 40. So 40 minus 2 minus 4 minus 6 minus 10 minus 12 will give us the frequency of orange, which is 6. And then 6 divided by 40 will give us the relative frequency, which is 3 over 20. So the answer is option A. Question 26A. Postcodes in Australia are made up of 4 digits. For example, 2040. Part 1. How many different postcodes beginning with a 2 are possible? So the smallest postcode beginning with a 2 would be 2000, and the largest postcode beginning with a 2 would be 2999, which gives us 1000 possible postcodes. Part 2. Peter remembers that the first 2 digits of a town's postcode are 2 and then 4. She is unable to remember the rest of the postcode. What is the probability that Peter guesses the correct postcode? So the number of postcodes possible beginning with a 2 and then 4 would be 100, starting from 2400 all the way through to 2499. So she would have a 1 in 100 chance of guessing the postcode on the first attempt, or 1%. Question 26E. The dot plot shows the number of push-ups that 13 members of a fitness class can do in 1 minute. Part 1. What is the probability that a member selected at random from the class can do more than 38 push-ups in 1 minute? So more than 38 push-ups means these are the people that need to be counted. So from 39 onwards, 1, 2, 3, 4, 5, 6, 7. So the probability will be 7 out of a total of 13 members. In part 2, a new member who can do 32 push-ups in 1 minute joins the class. Does the addition of this new member to the class change the probability calculated in part EI? Justify your answer. And of course, yes, the probability will change. Firstly, you've added another member. So instead of 13 members, there are now 14 members. And regardless of whether this member can do 32 push-ups or 40 push-ups, either way, the fraction has changed and it will not be equivalent to the original fraction. So since this member can only do 32 push-ups, the number of members that can do 39 or more, or greater than 38, is still 7, but there's now 14 members. So the probability, rather than being 7 on 13, it'll be 7 on 14, which is not the same as the original probability. Question 27E. A box contains 33 scarves made from 2 different fabrics. There are 14 scarves made from silk, S, and 19 made from wool, W. 2 girls each select at random a scarf to wear from the box. Part 1, copy and complete the probability tree diagram in your answer booklet. I've completed it here, so let me go through the explanation. This is a multi-stage experiment without replacement. So a girl chooses a scarf, does not put it back. So that reduces the number of scarves in the box. So if we're starting off with 33 scarves, so that's stage 1, when a scarf is chosen, regardless of whether it's silk or wool, that'll reduce the number of scarves by 1. So that's why the denominators of the second stage are all 32. So let's say a silk scarf was chosen first. So we're starting off with 14 silk scarves. That leaves 13 left to choose from. And 19 wool scarves still remain in the box. And another check is that if you add 13 and 19 together, it should equal 32, because the 32 represents the number of scarves that are left in the box. If a wool scarf was chosen first, that'll deplete the number of wool scarves by 1. So if we're starting off with 19 wool scarves, a wool scarf is chosen, we're left with 18. And there's 14 silk scarves left to choose from as well, because the wool was chosen first, so there's still 14 silk scarves remaining. I've also listed the 4 outcomes. So at the end of this multi-stage experiment, we've got silk, 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 wool, wool, silk, and wool, wool as our 4 outcomes. Part 2, calculate the probability that the 2 scarves selected are made from silk. So we want this outcome here, silk, silk. And we find that probability by multiplying 14 over 33 by 13 over 32, and we get 91 over 528. And part 3, calculate the probability that the 2 scarves selected are made from different fabrics. So we want the probability of either choosing silk wool or wool silk. And we just add those 2 probabilities together. So the probability of silk wool or wool silk is equal to 14 over 33. So this way, 14 over 33 multiplied by 19 over 32. I'll put that in brackets just to group it together, just to make it clearer, plus 19 over 33 multiplied by 14 over 32. And that equals 133 over 264. Question 1. Which of the following events would be least likely to occur? So let's work out the probability of these 4 events. So tossing a fair coin and obtaining a head, probability is 1/2. Rolling a standard 6-sided die and obtaining a 3, well that's 1 over 6. Randomly selecting the letter G from the 26 letters of the alphabet, we have a 1 on 26 chance of that occurring. And winning first prize in a raffle of 100 tickets in which you have 4 tickets. So that'll be 4 over 100, which simplifies to 1 over 25. So the fraction that's least is 1 over 26, and option C is the answer. Question 7. In an experiment, a standard 6-sided die was rolled 72 times. The results are shown in the table. Which number on the die was obtained the expected number of times? So each one of these outcomes has a 1/6 chance of occurring. So the expected number of times should be 1/6 of 72, which is 12. And the outcome that occurred 12 times, according to this experiment, is 2. So the answer is option B, 2. Question 10. Students studying vocational education courses were surveyed about their living arrangements. One of these students is selected at random. What is the probability that this student is male and living with his parents? Now, from the two-way table, we can see that 155 students were both male and living with parents. So to work that out as a probability, we take 155, we divide it by the total number of students surveyed, 505, and then we multiply that by 100 to convert that into a percentage. Like so. You end up with 30.693%, and that rounds to 31%. So the answer is option A. Question 18. 2 unbiased dice, each with faces numbered 1, 2, 3, 4, 5, and 6, are rolled. What is the probability of obtaining a sum of 6? Now, firstly, there are 36 possible outcomes. So 1 plus 1, 1 plus 2, 1 plus 3, so on and so on, all the way through to 4 plus 6, 5 plus 6, 6 plus 6. Now, we could do a two-way table, but that would take too long. So I think it's just easier to note that there are 36 possible outcomes. So let's see what the favoured outcomes are. So the favoured outcomes, for example, you could roll a 1 and then roll a 5. So 1 plus 5 is 6. Alternatively, you could roll a 5 and then roll 1. We could roll a 2 and a 4, so that adds up to 6. Or we could roll a 4 and then a 2. And of course, we could roll a 3 and a 3. So there's only one way that can happen. So there are 5 favoured outcomes. So the probability of rolling a sum of 6 is 5 over 36. So option D. Question 26C. The probability that Michael will score more than 100 points in a game of bowling is 31 over 40. So part 1. A commentator states that the probability that Michael will score less than 100 points in a game of bowling is 9 over 40. Is the commentator correct? Give a reason for your answer. Now this statement here, more than, does not include Michael scoring exactly 100 points. So we need to think about what is the complement of more than. Is it less than? Or is there something else we need to take into account? Now clearly, the complement of more than is less than or equal to. So the commentator did not take into account the probability that Michael scores exactly 100 points. So the commentator is wrong, since the complement of more than is less than or equal to. And the commentator does not take into account the equal to part here. Part 2. Michael plays 2 games of bowling. What is the probability that he scores more than 100 points in the first game and then again in the second game? So let's call this the probability of a win-win. So let's say that Michael scoring over 100 points is a win. And they're independent events in that the first game does not affect, or in theory does not affect, Michael's performance in the second game. So we can just multiply the 2 probabilities. So probability of a win-win is equal to 31 over 40. So that's the probability of Michael scoring more than 100 points. That's the first game, multiplied by the probability of winning more than 100 points in the second game. And that gives us 961 over 1,600. Question 30b. In a class, there are 15 girls, G, and 7 boys, B. 2 students are chosen at random to be class representatives. Part 1. Copy and complete the tree diagram in your answer booklet. Now I've completed the tree diagram already. I'm going to explain how I determined these fractions. Now we're starting off with 22 students, so 15 girls plus 7 boys. 2 students are chosen at random to be class representatives. That's without replacement. So when the first student is chosen, that student does not go back into the class to be chosen again. And that's why in the first stage, choosing the first student, it's out of 22. So we have 15 girls out of 22. That's the probability of choosing the first student as a girl versus 7 out of 22 being the probability for choosing a boy for the first student representative. But then when a student is chosen, we only have 21 students left to choose from, and hence why the denominator of the fractions in the second stage is out of 21. So if the first student chosen was a girl, we start off with 15 girls. That means there's only 14 girls to choose from. So the probability of choosing a second girl is 14 out of 21. But there are 7 boys still left to choose from. So if the second student is a boy, that'll be a probability of 7 out of 21 to choose that student, given that the first student chosen is a girl. Now, if the first student chosen is a boy, there's 21 students left to choose from. There are still 15 girls to choose from. So the probability of choosing the second student as a girl will be 15 out of 21. But if the first student chosen is a boy, that means we start off with 7 boys, we now have 6 boys to choose from. The probability will be 6 out of 21. Part 2. What is the probability that the 2 students chosen are of the same gender? Now the outcomes we're interested in are GG or BB. So to get the probability of GG, so 2 girls chosen, we take the probability from the first stage and multiply it by the probability of the second stage. And likewise for outcome BB, so choosing 2 boys, the probability of that occurring is 7 over 22 multiplied by 6 over 21. And here is the calculation. So probability of 2 girls chosen or 2 boys chosen is equal to 15 out of 22 multiplied by 14 out of 21. So that's these 2 probabilities there, plus 7 over 22 multiplied by 6 over 21. So this probability times this probability there. Add those together, and that equals 6 out of 11. Question 6. A cafe menu has 3 entrees, 5 main courses and 2 desserts. Ariana is choosing a 3-course meal consisting of an entree, a main course and a dessert. How many different 3-course meals can Ariana choose? I'm going to use a tree diagram to answer this question, and I've drawn part of the tree diagram already. So starting off with the entrees, we have a choice of 3, so call them entree 1, entree 2, entree 3. Now for each of the entrees, there are 5 main courses that Ariana can choose from. So 1, 2, 3, 4, 5. And likewise for E2 and also for E3. So we have a choice of 3 there. For each of the entrees, there's a choice of 5 main courses. And for each of the main courses, there are 2 desserts. And so on. So it's important to see the pattern here. So for every entree, there are 5 main courses, and for every main course, there are 2 desserts. So 3 times 5 times 2 equals 30. And the answer is 30 different meals that Ariana can choose. Question 8. A group of 150 people was surveyed and the results recorded. A person is selected at random from the surveyed group. What is the probability that the person selected is a male who does not own a mobile? So this is a two-way table. The first thing to note is the number of people surveyed, so that's 150. So the probability will be out of 150, but we may have to simplify the fraction perhaps, we don't know. Now let's select the correct cell. So we need this row, so male and does not own a mobile. So we need this column, and we then select the number 28. Let's put that in the fraction there. So it's 28 out of 150. And is there a 28 out of 150 there? Yes, there is. It's unsimplified, but that is the correct answer. Question 16. In Mattsville, there are on average 8 rainy days in October. Which expression could be used to find a value for the probability that it will rain on 2 consecutive days in October in Mattsville? Now this is an example of independent events. So on any particular day, if it rains, it does not affect or change the chance of rain on the subsequent day. So I've modeled this situation using a tree diagram. So let's say it rains on a particular day. The chance of rain is 8 over 31, since there are 31 days in October. The chance of rain on the next day is still 8 over 31. And to find the probability of rain on these 2 consecutive days, you multiply the probabilities. So it's 8 over 31 multiplied by 8 over 31. So it'll be option D. Question 19. Jazz has 2 bags of apples. Bag A contains 4 red apples and 3 green apples. Bag B contains 3 red apples and 1 green apple. Jazz chooses an apple from one of the bags. Which tree diagram could be used to determine the probability that Jazz chooses a red apple? Now this is a multi-stage event, so it consists of 2 stages. Stage 1 is to choose a bag, bag A or bag B, and there's a 50-50 chance of one or the other being chosen. So if you look at option C and D, the first stage does not refer to the bag or what bag to choose. So option C is out and option D is automatically out. That leaves us options A and B to choose from. So we have a 50-50 chance of choosing bag A or bag B for the first stage. Now the second stage is to choose the color of apple. Let's go back to the question. Bag A contains 4 red apples and 3 green apples, so that means there's 7 apples in total. And the probability of choosing a red apple from bag A is 4 out of 7. And if you notice with option A, so let's say Jazz chooses bag A, there's a 4 in 7 chance that a red apple would be chosen. If you look at option B, just for comparison, bag A, 7 out of 11, well, that doesn't make any sense because there's only 7 apples. So option B doesn't make any sense, and that leaves us with option A. Question 28A. James plays a game involving a spinner with sectors of equal size labelled A, B and C as shown. He pays $2 to play the game. He wins $5 if the spinner stops in A and 50 cents if it stops in B or C. Calculate James's financial expectation for the game. So let's think about this for a moment. James pays $2 to play the game, so he's already lost $2. However, if the spinner lands here in A, he's going to win back $5. If the spinner lands in B or C, he'll win 50 cents. So financial expectation is equal to the dollar win minus the dollar loss. So that takes into account the probability of winning the amounts shown, so $5 or 50 cents. And we know what the loss is already. So the loss is $2. And we can think of financial expectation as the average win or loss per game or per play. And we find this by taking the probability that the spinner lands on A and multiplying it by the amount won. So probability of A multiplied by $5 plus the probability that the spinner lands on B or C and multiply that by 50 cents minus the cost to play per game or any other losses in fact. But in this case, it's $2. And that's equal to 1/3 multiplied by 5 plus 2/3 multiplied by 0.5 minus $2. So just take into account that this 50 cents, we need to convert that into dollars. Okay, so we need to use the same units. And we find that the financial expectation for the game is $0, which means that on average, the win or loss is 0. Question 28C. A fair coin is tossed 3 times. Using a tree diagram or otherwise, calculate the probability of obtaining 2 heads and a tail in any order. Now it's a fair coin, which means the probability of tossing heads or tails is 50% or 0.5. That lends itself well to not just using a tree diagram, but other ways of listing the sample space. Now I'm going to use a 2-way table to list the possibilities, and it looks something like this. So the fair coin is tossed 3 times. So the first 2 times is represented by the columns, and the third time, or the third toss, is represented by the rows. So we have heads, heads, heads. That's one of the possibilities, right through to tails, tails, tails. That's the 8th possibility. So there's 8 possible outcomes. So we're interested in the outcomes that have a H, and a T in any order. So H, is out, of course. H, T is in. H, T, is in. And the only other one is T, H. So there's 3 outcomes, or 3 out of the 8, that have 2 heads and a tail in any order. So therefore, the probability of a heads, or tails in any order is 3/8. Question 16. The probability of winning a game is 7 over 10. Which expression represents the probability of winning 2 consecutive games? This is the multiplication principle in probability. I might just quickly demonstrate this using a tree diagram. Okay, so win, lose, win, lose, win, lose. And we want to win 2 consecutive games. So if the first game, the probability of winning is 7 on 10 or 7 over 10, winning the second game is also 7 over 10. Winning both games in a row is 7 over 10 multiplied by 7 over 10. And it's going to be option D. So you don't have to actually work out or evaluate it, just the expression is all you need. Question 21. 4 cards labelled 2, 3, 5 and 7 are placed on a table to form a 4-digit number. How many different numbers greater than 3,000 can be formed? So that means that the number can't start with a 2, but it can start with a 3, since if the first digit's a 3, the next digit can either be a 2, 5 or a 7, so it's clearly going to be over 3,000. So we have 3 different possibilities. So if the number begins with a 3, let's say, so I might just cross that out there, so let's choose 3, okay, as our first choice. We then have 3 more numbers to pick from. So in the 3,000s, we got a choice of 3 to begin with. So the next digit could be a 2, 5 or a 7. So pick one, you have 2 left. Pick the second one, you then have 1 left. There's 6 different ways. Now let's have a look at the 5,000s. So the numbers beginning with 5, 4-digit numbers beginning with 5. Again, same thing. We've taken out the 5, we've now got 3 left. So you choose one, and then you have 2 left. Choose another one, you have 1 digit left, and you only have a choice of 1, and that gives us another 6 ways. And then lastly, we have the 4-digit numbers beginning with 7. So if you choose the 7, right, you choose the 7, you have 3 digits to pick from. Choose one of those 3 digits, you then have 2 digits to pick from, and then once you choose one of those, you have, like your last digit, well, there's only a choice of 1, and that also gives us 6 total, 18 different numbers. So option C. Question 26E. The table shows the relative frequency of selecting each of the different coloured jelly beans from packets containing green, yellow, black, red and white jelly beans. Part 1. What is the relative frequency of selecting a red jelly bean? So relative frequency is basically the probability, but obviously determined experimentally, the sum of all the probabilities of all the possible outcomes should equal 1. So 1 minus 0.32 minus 0.13 minus 0.14 minus 0.24 should then give us the probability of red. So 1 minus 0.32 minus 0.13 minus 0.14 minus 0.24, and we get 0.17. And I might just fill that in the table here as well, just for completeness. Part 2, based on this table of relative frequencies, what is the probability of not selecting a black jelly bean? So this is an example of complementary probability. So the probability of not selecting a black jelly bean is the opposite of selecting a black jelly bean, or the complement of selecting a black jelly bean. So that's going to be 1 minus the probability of selecting a black jelly bean. And that's 0.14. So 1 minus 0.14 will give us the probability of selecting everything else. And that's going to be equal to 0.86. Question 30b. On a tray, there are 12 hard-centered chocolates, H, and 8 soft-centered chocolates, S. 2 chocolates are selected at random. A partially completed probability tree is shown. What is the probability of selecting one of each type of chocolate? Okay, thankfully, this one's very straightforward. So if the probability in the first draw of picking a hard-centered chocolate is 12 on 20, to pick a soft-centered chocolate should be then the complement of 12 on 20. So should, the two probabilities in each stage should add up to 1. So it's going to be 8 on 20. Since there are 12 hard-centered chocolates, 8 soft-centered chocolates, and out of a total of 20 chocolates. Now, we've drawn one of the chocolates out. How many chocolates are there left? There should be 19 because it's without replacement. So even though it doesn't say without replacement, it's assumed. 2 chocolates are selected at random. You don't put the chocolate back, right? So it's going to be now out of 19 for the remaining chocolates. Okay, because now there's 19 chocolates left, okay, in the box or in the tray. Now, if we've selected a hard-centered chocolate, so from there were 12 originally, how many do we have left? We've now got 11. So 11 out of 19, that leaves us 8 out of 19 soft-centered chocolates. This is for the second draw now, or the second stage. Now, likewise, for the first pick, or the first stage being a soft-centered chocolate, we've had 8 soft-centered chocolates to begin with. We've chosen one of these, then you've got 7 left. That leaves 12 hard-centered chocolates then to choose from. So I think a lot of the work is in just completing the probability tree. Once you've done that, let's now proceed to answer the question based on the conditions given, or whatever the favoured event is, which is selecting one of each type of chocolate. That means we can either have a hard-centered, soft-centered, so let's just put an asterisk there, or we can have choose a soft-centered and then a hard-centered chocolate there. So these are the two probabilities. So the probability of a H, HS, or SH, okay, hard, soft, or soft, hard, okay, is equal to, now we multiply along the probability, along the branches of the tree. So we'll do the HS first, so that's going to be 12 over 20 multiplied by 8 over 19 plus SH. So 8 over 20 multiplied by 12 over 19. Okay, so let's evaluate that and see what we come up with. Okay, so 12 on 20 multiplied by 8 over 19 plus 8 on 20 multiplied by 12 over 19. And we get 48 over 95. And that's approximately equal to, so we're going to convert that as a percentage. It doesn't actually say in the question to answer in percentage form. Always answer in fraction form, but let's just convert it into a percentage anyway, just sort of get an idea of what this is. So it's around 50.5%. Okay, so which is roughly 50.5% chance. Question 23. A group of 485 people were surveyed. The people were asked whether or not they smoke. The results are recorded in the table. A person is selected at random from the group. What is the approximate probability that the person selected is a smoker or is male? So first of all, let's have a look at the cells that represent the smokers. So we have this cell here and this cell there. Now let's have a look at the cells that represent males. So we've already selected the cell that contains 88, so we don't have to select it a second time, but there's also this cell here, 176, that represents the male non-smokers. So we add up all 3 of these cells together. So in fact, rather than wasting time writing it down, we could just do this. Okay, so 88 plus 176 plus 68, close bracket, and we're going to divide it by the total number of people, so which is 485, and let's multiply it by 100 to convert it into a percentage, and we get 68.45%. So again, that's option C. 28C. A cricket team is about to play 2 matches. The probability of the team having a win, a loss, or a draw is 0.7,
0.1 and 0.2 respectively in each match. The possible results in the two matches are displayed in the probability tree diagram. So part 1. What is the probability of the team having a win and a draw in any order? So first of all, we can discount the loss. Okay, so we don't include that. So win, draw in any order. So we've got win and draw. So we have this one there. So that outcome. And we also have a draw and a win since it's in any order. So we have this outcome here. So we multiply the probabilities together. So sort of along the branches of the tree. So 0.7 times 0.2. That's for a win and a draw. And 0.2 times 0.7 for a draw and a win. So the probability of win or draw, actually probably, maybe I'll write that win and draw in any order, is equal to these two outcomes that we've just identified. So 0.7 times 0.2 plus 0.2 times 0.7, and multiplying those together and adding them, 0.2 plus 0.2 times 0.7, and we get 0.28. Okay. Or 28%, but it doesn't ask for a percentage, so we can just leave it like this. Part 2, Paul claims that 1.4 is the probability of the team winning both matches. Give one reason why this is not correct. And hopefully you know the range of probability is between 0 and 1. 1.4 is not a valid probability as it is outside the range of 0, which is impossible, to 1, which is certain. So anything higher than 1 makes no sense. Question 29a. Two unbiased coins are tossed. Part 1. What is the probability that one coin shows heads and the other shows tails? So if you want to do just a quick probability tree, okay, so first toss, you've got heads, tails. Second toss, okay, you also have heads and tails. And it's an unbiased coin, so it's a 50-50 chance, so half-half, okay. What is the probability that one coin shows heads and the other shows tails in any order? So we could be talking heads, tails, so we have this outcome, or it could be tails, heads, which is this outcome. So probability of heads, tails is equal to half times half, which equals 1/4. Probability of tails, heads is again equal to half multiplied by half, which is equal to 1/4. So the probability of tails, heads, or heads, tails is equal to 1/4 plus 1/4, which is equal to half, or 50%. Part 2. A game is played in which one player tosses the two coins. The rules are as follows. If both coins show heads, the player wins $40. If both coins show tails, the player wins $20. If one coin shows heads and the other shows tails, the player loses $30. What is the financial expectation of this game? So in other words, on average, you're going to win, you're going to lose, and or by how much? So let's have a look at the wins. So the probability of showing heads on both coins. So if we go back to our tree diagram, probability tree, heads, heads, half times half is 1/4. Okay, so we've got a quarter chance or 25% chance of winning, so 1/4 of winning $40. If both coins show tails, the player wins $20. So that's again tails tails, same as heads heads. It's a 1/4 chance of that occurring, and we would win $20 if that was to occur. But if the coins show heads, a head and a tail in any order, we're actually going to lose $30. And there's a 50% chance or a 1/2 probability chance of that happening. So we're going to minus half times $30. And entering all that in, and you can enter it in as one expression. Let me just brighten the display a little bit and get the calculator in the right mode. Okay, so 1/4 multiplied by $40 plus 1/4 multiplied by $20 minus 1/2 multiplied by $30. And we get 0. So the financial expectation is $0. So we're neither in front or behind when we play this game on average. Question 5. In a survey of 200 randomly selected Year 12 students, it was found that 180 used social media. Based on this survey, approximately how many of 75,000 Year 12 students would be expected to use social media? So what we really want is the fraction of this 75,000 that's expected to use social media. And we need to use our sample to be able to determine that. So from 200 students sampled, 180 used social media. Now, that's the fraction of the 75,000 who are expected to use social media. Multiplying those together, 180 on 200 multiplied by 75,000, and we get 67,500. So that's option B. Question 15. The faces on a 20-sided die are labelled 5 cents, 10 cents, 15 cents, and so on, up to $1. The die is rolled once. What is the probability that the amount showing on the upper face is more than 50 cents, but less than 80 cents? So more than 50 cents means 55 cents, 60 cents, 65 cents, 70 cents, and 75 cents. So 1, 2, 3, 4, 5 outcomes out of a total of 20, since it's a 20-sided die. 5 on 20 is just 1 on 4, so the probability is 1/4, option A. Question 24. A deck of 52 playing cards contains 12 picture cards. 2 cards from the deck are drawn at random and placed on a table. What is the probability, correct to 4 decimal places, that exactly 1 picture card is on the table? So we can do a quick tree diagram, a probability tree diagram that is, to help us visualize this situation. So we've got picture card and non-picture card. Okay, so that's a P bar, which is non-picture card. We can draw another picture card, non-picture card, picture card, non-picture card. So this is an example of drawing a card without replacement. So to draw a picture card, we have 12 over 52. Non-picture card would be 40 over 52. That's 12 plus 40 gives you 52. Now, if we draw one card, we've got 51 cards left. So these probabilities are going to be over 51. And I might just do it here, over 51, over 51. Okay, so if we've drawn a picture card, it means that we've got one less picture card, so we're going to have 11 there. Okay, and non-picture cards, we're going to have 40 still left to choose from. Now, with this branch, we've drawn a non-picture card, so instead of having 40, we've now got 39. And we've still got 12 picture cards here. Now, we're asked for the probability of having exactly 1 picture card. So that's going to be P bar, so we need that probability there. Or P bar, P. So that's non-picture card, picture card. So those 2 probabilities. Okay, so that's going to be 12 over 52 multiplied by 40 on 51. And this one is 40 on 52 multiplied by 12 on 51. And we're going to add those two values together. Okay, so 12 on 52 multiplied by 40 over 51 plus 40 over 52 multiplied by 12 over 51. We get 80 on 221, 0.36199. So we need to round this value to 4 decimal places. So it's going to be 0.36120. In fact, the closest answer is going to be option D. Question 29C. A group of Year 12 students were surveyed. The students were asked whether they live in the city or the country. They were also asked if they have ever water skied. The results are recorded in the table. Part 1. A person is selected at random from the group surveyed. Calculate the probability that the person lives in the city and has never water skied. Now, with two-way tables, especially this kind of two-way tables, this is for non-mutually exclusive events, I like to add up all the rows, add up all the columns and get a total. And this will give us also the total number of people surveyed. So let's add up the first row, 150 plus 2,500, that's 2,650. 70 plus 800 is 870. Now adding up the columns, 150 plus 70 is 220. And 2,500 plus 800 is 3,300. Okay. Now what you should find is that if you add up that last row, okay, in fact 220 plus 3,300, so if you're under exam pressure and you don't trust yourself too much, just use your calculator, add them up, okay, you get 3,520. But also check that the column, the last column, also adds up to the same amount too. 2650 plus 870, you get 3520. So we're happy with that. Now we can answer part 1. A person is selected at random from the group. Calculate the probability that the person lives in the city and has never water skied. Okay, so lives in the city, that's this row, and has never water skied, that's this column. So it's 2,500 of those surveyed. So 2,500 over the total number of people surveyed, which is 3520. Okay. Okay, just enter into the empty calculator, and the calculator will simplify the fraction for you. So the probability is 125 over 176. Okay, so that was fairly straightforward. Part 2. A newspaper article claimed that Year 12 students who live in the country are more likely to have water skied than those who live in the city. Is this true based on the survey results? Justify your answer with relevant calculations. So what we need to do is compare kind of two subgroups, okay, or the two groups that make up this survey, this sample. So we have the city group and we have the country group. So let's have a look at the city group first. Okay. So the probability that they've water skied, okay, so lives in the city, we have 2,650 people. Okay, so probability that they've water skied. Okay. Okay, go back to the table again, just make sure we're doing the right thing. 2650, that'll be our denominator because that's the number of people that live in the city. 2650, and of those, 150 have water skied. We're going to convert that into a percentage to make comparison easier. Okay, so 150 over 2,650, multiply that by 100, and we get 5.66%. Okay. Okay, and it is actually approximate, so I'm just going to indicate here that it's roughly 5.66%. And what about country? Let's compare that group. The country group. Probability that someone selected, the student selected, that comes from the country and has water skied. Okay, so lives in the country. How many students that live in the country that were surveyed, 870. So that'll be our denominator, 870. Of those 870, 70 have indicated that they've water skied. So it'll be 70 over 870. We're going to multiply that by 100 to convert it into a percentage. And we'll just round it to 2 decimal places. So that symbol just means approximately equal to. You might have seen a squiggle like that as well. Okay, it means the same thing. So 70 over 870, multiply that by 100, and we get 8.05%. Roughly 8.05%. So the probability for country students is higher than for city students. Therefore, newspaper claim is correct. Anything to that effect or to that wording should suffice. Question 9. An experiment has 3 distinct outcomes, A, B, and C. Outcome A occurs 50% of the time. Outcome B occurs 23% of the time. What is the expected number of times outcome C would occur if the experiment is conducted 500 times? The first thing is, let's work out the percentage of time that outcome C would occur, or what percentage of the time outcome C would occur. That's going to be 100% minus 50% for outcome A and minus 23% for outcome B. So in fact, 100 minus 50 is 50, 50 minus 23 is 27% of the time. Okay, by all means feel free to use your calculator. Now, 27% of 500 gives you 135. So we expect outcome C to occur 135 times out of 500. During a year, the maximum temperature each day was recorded. The results are shown in the table. From the days with a maximum temperature less than 25 degrees Celsius, one day is selected at random. What is the probability to the nearest percentage that the selected day occurred during winter? So we're only interested in the days where the maximum temperature is less than 25 degrees Celsius. So in the table, we're only interested in this column. So the total number of days where the temperature is less than 25 degrees Celsius is 223, of which the number of days in winter where the maximum temperature is less than 25 degrees is 71 days. We'll multiply that by 100 to convert it into a percentage. So 71 over 223, multiply that by 100, press the SD button, and we get 31.83. So of the 4 options, the one that's closest to that is option C. Question 26a. Jeremy rolled a biased 6-sided die a number of times. He recorded the results in a table. What is the relative frequency of rolling a 3? Now the first thing we need to do is to add up the frequency column to find out how many trials were conducted. So 23 plus 19 plus 48 plus 20 plus 21 plus 19. So we get 150 trials. So the relative frequency is equal to, out of 150, rolling a 3 is 48. And if you wanted to, you could simplify the fraction. Why don't we? 8 on 25. Question 30D. A game consists of 2 tokens being drawn at random from a barrel containing 20 tokens. There are 17 tokens labelled 10 cents and 3 tokens labelled $2. The player wins the total value of the 2 tokens drawn. So part 1, complete the probability tree by writing the missing probabilities in the boxes. So from the start, the first token drawn, we have 17 10-cent pieces out of 20. That leaves 3 tokens left that are the $2 coins, or the $2 tokens, should I say. Now that we've drawn a token from the box, we now have 19 tokens left. So in fact, all of these probabilities in the second draw, or drawing the second token, will all be over a denominator of 19. So we can fill that out immediately, in fact, like so. But we need to work out the numerators though. If there are 16 10-cent tokens in the box, the sum must equal 19. There must be 3 $2 tokens in the box. So when you add the numerators, 16 plus 3 should equal the denominator of 19. Okay, what about these two here? So if we've drawn a $2 token, that means that we still have 17 10-cent tokens in the box. After all, we start off with 17 10-cent tokens, and on the first draw, if we draw a $2 token, we still have 17 10-cent tokens left. But there's now one less $2 token. Okay, so remember that we initially start off with 3 tokens labeled $2. That means we have 2 tokens left. So that answers part 1. Now part 2, technically, it's actually not in the syllabus anymore. It's actually a question from a previous syllabus. But I still think that it's worth going through this, and I've just added a little bit more to this. So part 2, considering that the game costs $1 to play, calculate the financial expectation of the game. So what this means is that how much on average would a player stand to win or lose. So we take into account how much it actually costs to play. So how much a player will win or lose on average based on these probabilities. So I still think it's a question that's well worth going through. So the way we work this out is we work out the probability, for example, of winning 20 cents, and we then multiply it by the value of that win. So I might just update this probability tree because I think this is going to help us definitely answer part 2. So winning 20 cents, I'm just going to write all of these in dollars. Winning $2.10, winning $2.10, winning $4. So I'm going to just express everything in dollar terms. The next thing we need to do is to work out the probability of each of these outcomes. Okay, and we can in fact just update this diagram here, this probability tree. The way we do that is we multiply along the arms of the tree, or the branches of this tree. So winning 10 cents and 10 cents, it's going to be 17 on 20. So you multiply the probabilities along the branches. Multiplied by 16 on 19, and we get 68 on 95. So that's the probability of winning 20 cents. So you can see it's actually quite high already. So what about winning $2.10? So 17 on 20, chance of winning 10 cents. And the second token being a $2 coin is going to be 3 over 19. And we get 51 on 380. We're going to use these probabilities to help answer part 2. Now, winning $2.10 again. Okay, so we have a 3 on 20 chance of getting the first token worth $2, multiplied by the second token, or the probability of the second token being 10 cents, which is 17 over 19. And we get 51 on 380. And lastly, to win $4, the probability of that is 3 over 20 multiplied by the probability of the second token being $2, which is 2 over 19. And we get 3 on 190. Okay. So the financial expectation, okay, I would say or we could say the average win or loss is equal to the probability of winning 20 cents. So that's going to be 68 over 95 multiplied by 20 cents plus the probability of winning $2.10. In fact, winning $2.10, we don't have to do this 2 separate times. We can just work out one of them and then just double it. So it's going to be probability of winning $2.10 or one lot of $2.10. So it's 51 over 380 multiplied by $2.10 multiplied by 2. Okay, because we have 2 lots there. And the last outcome, which is the win of $4, okay, and that's a 3 on 90 chance. So plus 190 multiplied by $4. But we need to subtract the cost of playing this game. It costs $1 to play. So working all that out now. Okay, so 68 on 95 multiplied by 20 cents plus 51 on 380 multiplied by $2.10 multiplied by 2, because there's two of these outcomes, if you recall, plus 3 on 190, okay, multiplied by $4, okay, and then minus $1 to play. And we end up with negative 23 cents. Okay, in fact, I'll just do it this way. Okay, all right, just write it like that. Okay, so this represents an average loss of 23 cents per play. And that's the financial expectation of this game. Question 20. A roulette wheel has the numbers 0, 1, 2, right up to 36, where each of the 37 numbers is equally likely to be spun. If the wheel is spun 18,500 times, calculate the expected frequency of spinning the number 8. So there's 37 numbers, each equally likely. So the probability of spinning an 8 is 1 on 37. Now the number of 8s that we're expected to get, assuming sort of a perfect world, every 37 spins, or in 37 spins, an 8 should turn up once. That's the expected number. So in 18,500 spins, right, the expected frequency is given by 1 on 37, which is the probability of getting an 8 in one spin, multiplied by the number of spins. 1 on 37 multiplied by 18,500. Which is 500. Question 25. A bowl of fruit contains 17 apples, of which 9 are red and 8 are green. Dennis takes 1 apple at random and eats it. Margaret also takes an apple at random and eats it. By drawing a probability tree diagram or otherwise, find the probability that Dennis and Margaret eat apples of the same color. Now, in situations like this, it doesn't matter whether it's two people choosing an apple each or one person choosing two apples. And the question is basically still the same. What is the probability of choosing two apples of the same color? And we're going to represent this with a tree diagram. So I'm just going to start it here. Our first choice, we can choose a red or a green. And our second choice, we can again choose red and green, and red and green, independent of what our first choice was. We can still choose a red or a green. However, the probabilities will differ. This is probability without replacement. So these are dependent events, in other words. In other words, your second choice depends on the probability of the second choice depends on what you got in the first choice. Now, originally we have 17 apples in the bowl. So the probabilities are going to be over 17. There are 9 red and there are 8 green. So the probability will be 9 on 17 for red, 8 on 17 for green. Now for the second choice, we've now depleted the bowl by 1 apple. So these are going to be probabilities over 16. So we've chosen 1 red apple already, which means we now have 1 less red apple. So that'll be 8 on 16 for the second red apple, or to choose the second red apple. Green apples though are still the same in terms of the number of apples. We have 8 green apples. 8 plus 8 gives us 16. There's 16 apples in the bowl. Now if we've chosen a green apple, the red apples are still the same number as originally, which is 9. However, we've already chosen a green apple, so instead of having 8 apples, we now have 7. So the two probabilities that we're looking for, the two favorable events that we're looking for, are the red reds or the green green. So they're the two apples that are the same color. So probability of red red is equal to 9 on 17 multiplied by 8 on 16. Probability of green green is equal to 8 on 17 multiplied by 7 on 16. What we do then is we add those two together. So the probability of red red or green green is equal to 9 on 17 multiplied by 8 on 16 plus 8 on 17 multiplied by 7 on 16. And let's do that now. Okay, so 9 on 17 multiplied by 8 on 16 plus 8 on 17 multiplied by 7 on 16. And we get 8 on 17 as the probability.
Question 15. The top of a rectangular table is divided into 8 equal sections as shown. A standard die with faces labelled 1 to 6 is rolled onto the table. The die is equally likely to land in any of the 8 sections of the table. If the die does not land entirely in one section of the table, it is rolled again. A score is calculated by multiplying the values shown on the top face of the die by the number shown in the section of the table where the die lands. What is the probability of getting a score of 6? So first of all, we have a 1 on 8 chance that the die will land in any of these 8 squares. So which of the squares are we interested in? We want a score of 6. So whatever number's on the top of the die, multiply it by the number on the square that it lands, that's the score. So if we want a score of 6, okay, we need the die to land either here. Okay, so we need to roll a 6 here. So I might just put a 6 there.
we need it to land here, or that's one of the other options. We need to get a number 3 rolled on the die there. The die could land on the 3 square, but the die itself would have to have a 2 on it, since 2 times 3 is 6, obviously. 4 and 5 don't count. Well, we can't get 6 by multiplying the number on the die by 4 or 5. The only other one is 6, okay? And we have to roll a 1 on the die there. So what's the probability in total? Now, the die is a fair die, so you have an equal chance of rolling a 1, 2, 3, 4, 5 or 6 on the die, and you've got an equal chance of also landing in one of these 8 squares. So, in fact, we've got 1, 2, 3, there's 4 probabilities here, okay, so it's like a multi-stage or a 2-stage event here. There's 4 different outcomes here that we're looking at, okay, and, well, multiplying those two together, okay, you have, let's say the die lands on the first square. We have a 1 in 8 chance, okay, of landing there, times a 1 in 6 chance of rolling a 6. Now, the same thing also occurs for square number 2. You have a 1 on 8 chance of landing there, multiplied by a 1 on 6 chance of rolling a 3. And likewise with this square here and this square there. So we've actually got 4 of these basically equally likely outcomes of landing on a square and rolling a particular number. Okay, so, or that event, should I say, is probably the better word to use. The event of landing on a particular square and rolling a particular number. Okay, now multiplying all that together. Okay, so make sure we do this properly. So 1 on 8, okay, multiplied by 1 on 6. And multiply that by 4, and we get 1 on 12. Okay, so it's option B. The other way you can do this, okay, so is you can draw a tree diagram, perhaps. Okay, there's actually, sort of that's the other way, I guess, and if maybe there might be other ways too, I don't know, but this is probably the easiest. If you want to do a tree diagram, you could do it this way. So 1, I have to do it a little bit larger, 2, 3, 4, 5, 6, 7, 8. Okay, each of these is a 1/8 chance. Okay, these are the squares. Okay, one of the 8 squares, and so on. Now, there's only 4 that we're interested in. 1, 2, 3, 4. Okay, so, and we need to either roll a 1, a 2, a 3, or a 6. 1, 2, 3. Now, you can see that drawing the tree diagram is going to be too messy. Now, that's one of the reasons why I just wanted to show you this, to think, well, if you've gone the tree diagram way, you'd probably hit a dead end at this point. And you probably think, nah, this is getting far too messy. You could probably do it, actually, and there's enough space on this page to do the tree diagram. But I think it's far easier to think of it as like a compound event or a compound sort of outcomes where you know the probability of landing on a square, and you also know the probability of rolling a particular number, and the two outcomes are multiplied together to give you the probability of that particular event. Question 11. There are 8 chocolates in a box. 3 have peppermint centers, P, and 5 have caramel centers, C. Kim randomly chooses a chocolate from the box and eats it. Sam then randomly chooses and eats one of the remaining chocolates. A partially completed probability tree is shown. What is the probability that Kim and Sam choose chocolates with different centers? This is a multi-stage event without replacement. In the first stage, there are 8 chocolates to choose from, 3 of which are peppermint, 5 of which are caramel. So the probability of choosing peppermint is 3 out of 8, and the probability of choosing caramel is 5 out of 8. In the second stage, there are 7 chocolates to choose from. The probability of choosing peppermint, given peppermint was chosen first, is 2 out of 7. The probability of choosing caramel, given peppermint was chosen first, is 5 out of 7. The probability of choosing peppermint, given caramel was chosen first, is 3 out of 7. And the probability of choosing caramel, given caramel was chosen first, is 4 out of 7. Now we're interested in the probability that the 2 chocolates chosen were of different centers, and that can occur in any order.
So the two outcomes that we're interested in is peppermint caramel or caramel peppermint. So the probability of peppermint then caramel is 3 out of 8 multiplied by 5 out of 7, which equals 15 out of 56. And the probability of caramel then peppermint is equal to 5 out of 8 multiplied by 3 out of 7, which equals 15 out of 56. So the probability that the two chocolates chosen were of different centers is equal to the sum of these two probabilities. So that's equal to 15 out of 56 plus 15 out of 56, which equals 30 out of 56, and that simplifies to 15 out of 28. So therefore the answer is option D.